Okay, let's pick up where we left off. When we left off last time, we were talking about how sum of squares had a problem, and the problem is it does not take into account sample size. And we looked at an example where two distributions have the same sum of squares value, but they look pretty different, quite different. And you can kind of look back on A and B to see what I'm talking about there. So if we have this problem with sum of squares, there is another statistic we can use, and that is the variance. So the formulas for variance, there's one for the population variance and one for the sample variance. And I'll tell you, the population variance is really not used very often. Because if you think back to sample selection, and to be able to calculate the population variance, you have to be able to identify every person in your population, which is not always easy. But the symbol for population variance is this. It's the sum of your squared deviation scores, which is also known as sum of squares. So sum of squares divided by big N. So if you have capital N, that denotes your population. If you have a little n, that indicates you're talking about the sample. And this sample variance formula is the one that we're going to use. Population variance, you'll see it in some instances, looking at different things that we'll look at along the way. But for now, we're just going to focus on the variance. So, confusingly, the symbol for variance is little s squared. You would think it would be v or v squared, right? Nope, not going to make it easy on you. The sample variance is little s squared, but you'll see why in a few minutes. So again, it's still something we are familiar with. It's the squared deviation score, or our sum of squares. But this time we're going to divide by n minus 1. Now, I'm not going to ask you to memorize this formula. If you need it, I'll have it for you, or we'll ask SPSS to calculate it for us. So we're not going to worry about memorizing it, but I do want you to know what's happening in the formula. Okay? So again, we have the sum of our deviation scores squared divided by our sample size minus 1. So again, this is sum of squares, and sometimes you'll even see variance denoted like that. They'll say sum of squares divided by n minus 1. But I guess this is the more official formula. So either way. But again, this symbol for variance is s squared. All right, so let's think about some questions. One of these we're going to hold off on. What are we doing when we divide by n? Anytime you divide by n, what you're doing is you're removing the influence. Removing influence. Well, that's terrible writing, but you get what I mean. Okay, when we divide by n, we're removing the influence. This question we're going to wait on, and this one we're going to talk about. So why do we divide by n minus 1 for the sample variance? So remember our formulas, how they differed? Here's our population where we just divide by the number in our population. But with sample variance, we want to divide by our sample size minus 1. So the question becomes, why n minus 1? Why not just little n, or sample size? Okay, so I want to think through this question with you, because I think it'll help you understand variance a little bit as well. So imagine this situation. So say we have a population, and I'm going to just say POP for population. So this is our population. It has a mean of 75, and the symbol for mean of the population is this mu. So it has a mu of 75, and then the curve looks about like this. So from this population, I want to pull a sample. All right? I'm going to pull a sample. I'm going to say pull sample. Maybe I'm conducting a study of number of times people click on Facebook during a day. All right. So in the population, the mean is 75, but maybe I want to sample from that population because I feel like my area clicks on it less or more or whatever. So I'm going to pull from that sample, from that population. I'm going to pull a sample. Okay. So say I pull a person from here and ask them, how many times do you click on Facebook a day? All right. Where do you think that score is likely to be? Okay. It's probably going to be somewhere around 75. So let's think about why that is. If this curve denotes people, right? So these are all people scores. So this is the number of times they click Facebook in a day. And we have been able to identify and measure everybody. All right. Which I'll just say to the side, if you can identify and measure everybody, you don't need to do statistics. You can just report what the population is. But let's ignore that for just a second. So imagine you pull someone out of that sample. Because there are more people or more scores here kind of under the hump, if we randomly pull somebody out of the population and ask them that question, it's probably going to be somewhere around here. Can you see that? Okay, so say we do it again. Maybe they're over here now and over here now and here. But generally, since we have the biggest chance of pulling people out of this area and less of a chance of pulling one of these people in the tail, we're probably going to get something right around the mean like this. Okay? And not so much out to the side. So say we have a sample of 30 or 40. And now I'm looking at this distribution. So this is my sample distribution compared to my population distribution. Okay? Which one of these, the population or the sample, is more spread out? Right? So we have these people here under the curve, and we have these people under this curve. All right, so our sample is less spread out. Our population is more spread out. So less variability, more variability, right? Can you see that? So when we divide by n-1, we are trying to correct for this. All right, so our sample variance, which is s squared, right, is going to be less than our population variance. Okay, so we're going to have an underestimate of what's actually going on in the population. Okay, so when we pull a sample, we really want it to reflect the population, right? Because we want to see what's going on in the population, but I don't have the time or the money to check everybody in the population, so I'm going to check this smaller sample, but I want it to be reflective of the population, right? So what I'm doing when I divide by n-1 is I'm recognizing that my sample variance is going to be an underestimate of the population variance. Okay, does that make sense? The sample variance is going to be an underestimation of the population variance. So think about when you divide by a smaller number. Let's take just a couple of fractions. So if I have 1/3, what does that equal? 0.333 repeating. We'll just say 0.33. Now, if I divide by a smaller number, say 1/2, what happens to my answer? It gets bigger, right? So if I'm trying to correct for this underestimate of the population variance, if I divide by a slightly smaller number, I'm going to essentially give myself a little boost. So that's what I'm doing. I'm trying to correct And first I acknowledge that my sample variance is going to be a little less than it probably is in the real population. So knowing that, I'm going to divide by a smaller number to give myself a little bit of a correction or a little bit of a boost as far as my variance goes. So that's why we divide by n minus 1 for the sample compared to just plain n for the population. Okay? So let's continue here. Why does the n minus 1 correction yield less correction as n gets bigger? So remember that n here, n is your what? N is your sample size, right? So we said that n minus 1 is a correction factor, just like it says over here. So why does my correction factor get less? Why does it yield less of a correction as n gets bigger? Because larger samples come closer to representing the entire population, and therefore the sample variance will better reflect the population variance, or because we never measure entire populations, because increasingly smaller samples will tend to yield increasingly larger variances than the population, because we never measure entire samples, or none of the above. Right? What's going to be A, or the first one up here, because as our sample gets larger, we're going to start looking more and more like the population. So we're going to need less and less of a correction. Does that make sense? If our sample is supposed to reflect the population, as our sample gets bigger, it's going to do a better and better job of reflecting that population. So we're going to need less and less of a correction. You could have also guessed this because this is the longest answer choice. Sometimes that's a real giveaway. So these are not really very good distractors down here. I should go back and rework those. But anyway, we're going to look more and more like the population. Okay, some things to note. All right, so this is what we were just talking about, that correction being less critical. If your sample size, so this little n is your sample size, is significantly less than the population, the correction is more critical. Now, that's intuitive, right? If this first one is true, then the second one is pretty much the opposite of it, right? So that makes sense. Are there cases when you can divide by n rather than n minus 1 and not have bias, right? And there are just a couple of cases. If your population is a uniform distribution, so what that means is, looks something like this. No matter who you sample, it's going to be identical to the population. Or in a case where you have no variability, so what that means is everybody scored the same. So you're just looking at a tower of scores, everybody having the same value. So it's not going to matter if you divide by n or n minus 1, because when you pull your sample, it's going to look identical, right? So I guess that the answer here is, if there are cases where the population is distributed in such a way that no matter who you pull, your sample is going to be identical. So if this is the population and this is your sample, no matter who we pull, these two are going to look identical. So those are really the only cases. And if you have a weird population distribution like that, you're probably not going to be pulling a sample anyway. But it is something to consider when we're already thinking about this n minus 1 issue. All right, so let's look at what's wrong with variance, because there has to be something wrong with variance, right? We went from mode to median to mean because there was always something wrong with one statistic. We went from mean to spread outness to range, which had an issue. Sum of squares had an issue, and variance has to have an issue. So the biggest problem with variance is it's hard to interpret. Because if you remember, even our symbol, if you forget, you can look at the symbol and tell, but it's in a squared metric, right? So it's squared. So whatever our variance turns out to be, maybe it's 9. This is hard to interpret because it's squared. So imagine the variance. You're looking at a group of kids, and on a spelling test, the variance of the number, so let's say the number of words missed, if that variance is 9. So it's very hard to interpret. If we want to figure out how spread out that variance is, we're going to have to unsquare that 9. So that would be 3. So on average, kids are missing 3 words around the mean number of words missed. So if this is the mean, maybe on average they miss 1 word. So on the mean number of words missed is 1. On average, they're scoring 1 plus 3 is 4. 1 minus 3. Okay, so see, that's not going to work because that's going to be -2. Maybe they get some bonus words. But anyway, you can kind of see that unsquaring this variance is not very friendly, not very user-friendly. So to combat that problem, we're going to use something else. And that's something else I'm going to talk about in the next video.